to ísť.
Akože podľa mňa je to super po anglicky, ale to bojím sa, že by som niečo nepochopil, by to zdržovalo ľudí, že sa pýtali, čo znamená.
To, že sa nejaká hodina zdrží, chlieb nebude lacnejší, nebude drahší. Nikto mimo tejto miestnosti si to nevšimne. Môže sa niečo naučíte. Okay, let's try. So, what's probability? What have you learned in your high schools or at your university? What is the probability? What would you say? And you can also translate the English, the Slovak expression on the slide to English, and even say something. I think that probability is this and that.
Could be said that it is a chance of something happening.
Chance of something happening. Okay, very good. Some other opinions, ideas. It's good. What does the Slovak say? Probability expresses a possibility that some event will happen, right? So we have this standard example that you have seen in your high schools, maybe at the university, somewhere, maybe in the kindergarten, because you were trying to play the game with some dice, yeah? In Slovak we say človeče nehnevaj sa. How is it in English? In German I used to know that. Okay, so we can start by continuing our discussion. What did we somehow mentioned last time when we were talking about throwing the dice? If I know the initial condition and I know all the forces that I will use to throw this dice, I can use Newton's laws and calculate where it will land. I can easily find out what is the outcome of this event of throwing the dice. So what's probable, what's uncertain about this? Čiže čo je teda neurčité, kde je tá náhodnosť? Why is the dice throwing a die one of the first examples in probability? Yeah. It's quite hard. Well, if you have tried to play whatever game with dice, and you were trying, for example, to throw 6 on the die. Yeah, it's quite hard. Yeah, I think all of us were trying at some point in life, because it's hard to get the initial condition, the force to actually force the die to land on some specific number. And whenever there will be some complex phenomena, some phenomenon that we cannot describe, for example, cannot describe easily or cannot calculate easily, for example, with the physical laws, like we did in the class of modeling in process industry, then the probability is one thing that we can rely on. Because what will this graph say? Last week we were having the histogram as one of the plots, which is useful. You saw it in your exercises. So here we will be building a histogram. We will have the outcomes of our throwing of the dice. So it will be either 1, 2, 3, blah 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 until 6, and here we will count how many times will we get which number. So if we start by throwing the dice, of course, I should have put this MATLAB code on the eLearn page. I will put it. I just generated some random numbers. So first try is 5, second try is 6, the third throw is 1, and so on until 10. Okay, until 20. Sorry. well, what can we say now? So this is our data. This is the data that we obtain. What did we expect will happen, and what happened? Why is it not maybe what we expected?
Well, in theory, the more times we throw the dice, the percentage of a chance of a certain number, well, it should spread out evenly.
Yeah. Or the real chance, the real probability will somehow materialize. You will find out exactly. So we are talking here about really something that we need to repeat in order to observe. So in short, basically, we need a lot of data to have some idea about what is happening in our system. But okay, so let's continue. So how much? How many data? This is 100 throws. It starts to where should we expect that will be this level? Which number? What would we be expecting from this experiment? That all the columns will have, if I have 100 throws, then I should have 100 divided by 6, right? Because I have the equal probability. 100 divided by 6 is somewhere here, right? We are getting pretty close. So what if we try something more? So what does this graph show? This graph will take the previous outcome of the 100 throws, will place them here, and here is our histogram. If we would have continued to throw the dice another 900 times, so we have 1,000 throws of on a dice. So we are getting close, but there are some outliers. It still doesn't look like the outcome that we are expecting. 10,000, 100,000, and million. And million is already quite good. Yeah, we already see that what Rado was saying, that we will get an equal chance of each number. If the dice is fair, we will get the equal chance of each number appearing. Just to calculate this even easier, this is 6 million tries. Why? Because now I have 6 million tries all together, and now I see that each number was the result of the throw, approximately in 1 million cases. So how do we calculate this probability? We already feel it. What is the formula? Try it in English. Now, number of the outcomes that we are looking for, and number of all outcomes, or number of all trials. Yeah. So, number of occurrence of a, what is yaw in English? Whoa, this is even harder than I thought. Phenomenon divided by the total number of the occurrences of 1, 2, 3, or 6. Good. So this is the 101 or hello world example to the probability. What if we now go to 2 dice? That's the correct plural. 2 dice, and we will not be looking at each of the dice individually, but we will add together the result. So if we have 6 and 6, our result will be 12. What are the probabilities there? What is the probability that I will throw 1?
Throw 1, 0%.
Perfect. Also 13, yeah? Very good. So if I continue, what is the probability that I will throw number 2?
That's just one option.
There is just one option over.
36 is all.
Exactly. Where is it? Here it is. Yeah. So if the outcome of this throw is 1 and 1 on the die number 1, die number 2, well, there is only one of the possibilities that the sum will be 2. Another extreme is the number 12. I only have one option, but if we look, for example, for the number 7, there are already a couple of options. Yeah, number 1, number 6, number 2, number 5, and so on. So quite intuitively, if I will now try to form a histogram similar to the previous example, but now I will be looking at the sum on the two dice, some of the numbers. There some of these sums will be more probable. So it should look something like this. Yeah, the smallest probability for 2 and 12, largest for the 7, and so on. Makes sense, right? And now this is the standard example for introducing one of these most famous curves in mathematics. If I have 3 dice, if I have 4 dice, so you can just observe, I mean, before we had the largest probability of throwing 7, so if I have 4 dice, just have 2 and 2, so now we have largest probability is 14, we cannot throw a number which is less than 4 or greater than 24, and I can continue. That's 8, 9, 10, 11, 12. These histograms are getting very, very nice. And we stop at 20. So what is the curve that this looks like? Gauss curve or bell curve, because it looks like a bell you put on Christmas tree or so. Yeah, exactly. And Germans are a special folk which put mathematics on their, which used to put mathematics on their money. So this is the 10 Deutsche Mark with Mr. Gauss as a photo, and with this curve, even with the formula. Crazy folks, German, yeah. They put mathematics on the money. Good. So what? Yeah, this is even zoomed in. So what does this formula? And there are pretty specific things about it. So tell me now, how many of you don't know, never saw this equation, this function in a mathematical form? Only one? So everybody knows. So tell me what is, for example, the sigma?
Well, the question wasn't if I know to explain it.
Good one. Oh, you caught me on that. Good one. Okay. So let's put this function into our whiteboard and see what it all does. Okay, so we have f of x is equal 1 over square root of 2 pi, now e to the power of minus x. Number of replications, number of no, there is no such thing, but it's a good comment. Okay, there is mu, so I'll put mu. x minus mu square divided by 2 sigma square. Fine, fine. You can go away now. Okay, so this function, it was written on the banknote there with the Carl Friedrich Gauss. It was written or called with a lowercase f. Its name is can be also nicely shortened to PDF, which doesn't mean portable document format, but it means probability density function. Probability density function. And as we got this function from some throwing of the dice where we were plotting these histograms, and this function will represent histogram in its continuous form, it represents the relative probability, or better name is the probability density. In Slovak it's called pravdepodobnostná funkcia. Just for the reference to the Slovak literature, because some of these translations are not always best, or not always one-to-one match to the English. Pravdepodobnostná. Okay. Good. Where am I? Good. Yup. Hi. And we would say, we started to lecture in English, and we would say that an event X, and it should be capital X, obeys normal distribution, or I should say normal or Gaussian distribution and all its uncertainty, all the probability will be basically hidden in these two numbers, sigma and mu. And that's why we would say this sentence will be written in mathematical terms as x, this kind of tilde. There will be the somewhat calligraphic capital N, and we will have the two. What did I do? We will have the two parameters, which is, one of them is mu, and the other one, some people write sigma, some people write sigma square. I think sigma square is more occurrent, more dominant. So this will tell us that we have some value of the number mu, some value of the number sigma square. So those of you who saw this function, recognize it. Can you recall what the mu is? What the mu stands for? Mean value. Yes, exactly. Mean value, stredná hodnota in Slovak. Usually it will be something related to the arithmetic mean. Expected. Also, some people say it's expected value of x and the sigma square. You saw it definitely in your lab exercises from physics. Variance, exactly. Sigma square is variance. Its square root, so this sigma here will be what? Ah, perfect. Okay. In Slovak it's either štandardná odchýlka alebo smerodajná odchýlka. Standard deviation. Rozptyl. Thank you. Very good question. Yup. Good. So let's try. I remember when I saw this function for a first time, and it's. I give you that it's a bunch of numbers. There is Euler constant. There is pi. There is square root, and yeah, many different terms. So let's try to break it down into other terms. So let's do it like this. We will have our f of x 1 over sigma square root of 2 pi. You might be wondering what the 2 pi stands for. Why is it there? We will get to that point. And this is multiplied with the e to the power of I propose to change slightly the notation, as I do not like the Greek numbers so much, and the x with the bar on top is pretty standard. You also had it definitely in your physics laboratory. Okay, so let's try to see some very specific yet very standard case where our mean value of x will be 0 and our either variance or standard deviation will be 1. So can you tell me what it will look like, such that you practice the English pronunciation? If I plug in 0 for x bar and 1 for sigma, or sigma square, that's the same thing.
1 divided by the root of 2 pi.
Yeah, the square root of 2 pi, exactly.
Multiplied by Euler's number.
E to the e to the minus, and you can continue. You can say e to the power or e to the, that's understood. X square.
Divided by 2 times sigma.
Yeah, sigma is 1. Yeah, so okay. So we simplified it at least a bit. We could have also tried something like sigma squared to be 1/2. We would get rid of these two here, but we would have. We would also get rid of the 2 here. Doesn't matter much. But what we can do now is to see how this function is composed of of several terms. So it's function of x. X is here squared. So how does the function x x squared or minus x squared? X squared is fine. So the function x squared, how does it look like? Of course, it doesn't have negative values, and around the value 0, so around the what we will call later mean value, it will have minimum, right? And it's parabola, yeah. It's nothing surprising. Good. So let's now continue. Well, we can, of course, inverse our parabola. So we can, for example, plot this function, negative x squared divided by 2. How will that one look like? So that one will have only positive or only negative values? Only negative values, such that just to know where should I put the 0, and well, it will be just flipped horizontally, yeah. Don't wanna draw it too thick, because I wanna continue drawing after that. All right, now comes the hardest part. So the hardest part. Now we only need to take this shape and transform it with the exponential function. How to do that? How would you think about this? What would be your first step or first analysis? Okay. So we will transform all these negative values to positive. That's a good start. So now we have the minimum. And if we have minimum, what about having a maximum? Can we have a maximum? That was fast answer, but what? Yeah, go on.
It can go to infinity function.
X can be number, so x.
Okay, I give you that. But let's see, so let's just maybe draw e to the y, such that we are not messing with our notation. What is particular about the function e to the y if I'm plugging only negative values? How does the function look like? Draw it in the air with your hands. So, and for the negative infinity it goes to 0, yeah. And for the positive it goes to positive infinity, but on here it is bounded. So on the left hand side we have the left hand side we have the asymptote which goes to 0, and if we are only in the negative values, what is the value here? So that would be our maximum. Correct? We are taking, yeah, these are minus x squared divided by 2 is either 0 or minus 1, minus 2, blah, blah, blah. So those are the values which are just landing here on the left-hand side. So our function e to the that fraction can only be at minimum 0. Yeah, that's the asymptote here, and at maximum it can go to 1. You will try plotting this in your exercises. So of course, where would our mean value, the value in the function value in the mean value land? So it's 0 for x squared divided by 2, so it will be 1 for the e. Áno, sme iba v tomto ľavom intervale. Nikdy nám nič kladné nepríde. No nemôže, pretože sme si tu povedali, že minus x na druhú lomeno 2 je stále záporné. Alebo nekladné, ak by sme to povedali ešte správnejšie. Čiže 0 alebo záporné. Počkaj, čiže hovoríte, že tu mám mať mínus a nakresliť tú funkciu naopak? Tým pádom by sme boli v pravej časti. OK. Môžeme to nakresliť aj z toho, ako je dve strany tej istej mince. Hej, dobre. Let me know. So that one would go like this, right? Yeah, if we would start, this is more like starting from this x squared, which is only positive or non-negative, 0 and positive, and we transform it to something e to the minus its value. Okay, so now the function on the very right cannot go to infinity like our previous functions, so it will kind of curve, and we will get very surprisingly this bell-shaped curve. Let's try another time. Okay, this is probably the best I can do. And that's already our histogram. Yeah, it's in principle it's very silly exercise that we just did, but maybe it helps you to somehow connect that picture on the 10 Deutsche Mark banknote to the actual mathematical representation. What would be the natural question now? Concerning that we have done this for just a very, very simple example. Well, will this work even if we have, let's try some different color, even if our mean value is equal to 1? So how will it work? What would happen to this one, to the parabola? So how would the function x exactly, yeah. So we are talking about the function x minus 1, which is if we plug in x minus x bar, where x bar is 1. So this function will be shifted to the right. It will have its minimum in the value 1, but basically nothing else changes. So if we flip it, that was our exercise. we'll just get the very similar function, and if we just apply this exponential transformation, well, again, very same story. Let's see how did I get better with throwing these bells. So our histogram will be shifted. Our histogram will have the value with maximal probability. That was the best probability that we had, for example, when throwing these multiple dice. Our histogram will be centered at this value. We will have the highest probability there. Okay, what about some different value of the sigma? So let's say, which one, sigma or sigma square? I would go for sigma. So now we will have the, let's say, still the case where our mean value is 0, but our sigma will increase. What are we talking about here? This is the function. This one stays the same, right? Where did we plug the sigma in this example? On the left or in the middle? In the middle. Yeah, but can't we actually have it on the left? Because if this is divided by 1 square divided by 1 square, because you will recognize its action better here. Yeah, so we will not lose anything if we now say that we are plotting not x squared divided by sigma square, but sigma square, right? Yeah, so our mean value is still 0, plugging 0 here, so I have x squared in the numerator, and I ignore this 2 for a while, and I plug in the value of the sigma. Sigma square is 4. So how would this function look like? What will be the remarkable difference? Everybody here sees that it will be wider, or should we just have 2 more sentences? Why is it wider? Okay, I don't know, briefly, if I have this black function and I evaluate x squared at the value of 1, I have the functional value 1 squared is 1, yeah? So there is 1 here. If I now evaluate this yellow function, which I still haven't plotted, well, what should I get? 1 squared is 1, I should get the value of 1/4, 1/4, yeah? So if I had 1 here, so 1/4 will be somewhere here. That's why our, maybe it's too wide. Yeah, that's why this is how the parabola divided by 4, x squared divided by 4 will look like. Same story in the middle. That's just the flipping. and on the left we should also get to something wider. Let's see if I can make it. Yeah, something like this. You will plot better, nicer, and more informative pictures in your exercise. Good. Well, we still haven't really resolved why the hell do we have this fraction here in front of this exponential? Because the exponential seems to be working. We already get something which looks like our histogram of the 20 dice. So why do we need it? To answer that, we need another function, second and the last new function for today. Maybe even the first one wasn't new, maybe even this one. So if we had PDF, probability density function, now we will have CDF. And this is called cumulative CDF, cumulative, and it's not it's not density, it's cumulative distribution function. Of course. X na druhú lomeno 8. Dobre, to záleží od toho že čo si kreslíme. Kde si? Keď si povieme, že tu si kreslíme takto. Ja viem, rozmýšľam, ako to tam nakresliť, aby to bolo jasné. Ale tuto som to nenakreslil práve jasne. Takto. Kebyže si povieme, že tu na tomto obrázku si kreslíme ten čitateľ, menovateľ, ale nie tú dvojku. Ale iná správna poznámka, čiže áno, tuto je to 8, tu už by to malo byť ešte širšie. Ale je to moja umelecká licencia, koľko mi tabuľa dovolí. OK, good. Good. So our second and last function for today is cumulative distribution function, CDF. In Slovak we would say distribučná funkcia. Distribučná. Okay, and it's very much a sibling, sister or brother of our PDF. They are one mirror image of another. So if we have PDF and the CDF, we would be, if as it was on the German banknote, if we say or denote PDF by the lowercase f, then usually standardly in the literature you will find that the CDF will be capital F. It's not a Laplace image of or Z transform image of the F. And what is nice about the CDF, why we need it, it actually expresses the probability. So this is the probability as we P or PR, some people write it, or probability. While the PDF probability density function was only relative probability density. We will see the difference in a second. Density. Good. Anybody knows what is the CDF? What is the cumulative function, cumulative distribution function? Let's have its definition. We will need, so far we were using x as our variable, x as the outcome of some random event. We will have a z here, but it will live in the same world as x. I will show it now. So the value of the cumulative distribution function at the point z is the probability of x, that was the outcome, the random temperature in this room, or the outcome of throwing dice, x being less or equal z. So probability of x being less or equal z, and it will be calculated, maybe for some of you in a horribly looking manner. We have some integral, and we will integrate the PDF x. So what we'll do, we will, in principle, this means what? The integration will go from -infinity to the value of z. So we are kind of scanning our bell curve. We are scanning our bell curve from -infinity until some point, and we are adding all the values that we encounter. Let's maybe, before we jump into it, let's have where is this guy? Let's have some analog in throwing our die, even the single one. This is the question of asking, what is the probability that the number I will throw on a die is less or equal 3? And you would simply answer, well, less or equal 3, the possibilities are 1, 2, 3, and I have 6 possible outcomes, so it's 3 divided by 6, or 1/2, or you just count 1/6, 1/6, 1/6, 3/6 is also 1/2. Now, why does this look so strange at the first sight? Because here in this world of discrete probability, we were living in a world of having just finite number of outcomes. Yeah, 1, 2, 3, 4, 5, 6. But now, if we want to live, where does this flip? Get lost. Okay, good. Now, if we wanna flip ourselves to the world where this is, for example, temperature in this room. Well, the temperature in this room will not be 25.15 degrees and then 25.75 degrees. No, it has continuous values. So in this world, it stops to make sense to look at probability density function and infer some probability, because in principle the probability of measuring, if I just put the thermometer here on and I measure 22.777777 degrees, and I'm asking what is the probability that I will measure this one, the probability is 0. Because, I mean, there is infinitely many decimal places, so there will be just 0 probability that I will get this exactly the same outcome. But then it would make sense to ask things like, what is the probability that the temperature in this room is below 15 degrees? Or what is the probability that the temperature in this room is between 15 degrees and 25 degrees? That already makes much more sense, even if you think about some control application, what's the probability that my control output is plus minus 5% from my set point value. Yeah, so this is the relatively hard thing if we are transferring from this world of throwing dice, throwing some coins, because then we have only discrete outcomes. But it's not a problem. We can very easily live with it. Good. So let's try to see how would that work. Let's try to have our PDF. What is our PDF? That one lives in the variable x, and this is the bell curve. Yeah, something like this. Here we have our mean value. We can. Do we need to make some value assumption? Not yet. So this is our PDF. How would our CDF look like? In principle, if the CDF
So this might be right side of this function because x is lower than z.
x is lower than z.
Same x down like this x given the probability.
Once more, I don't get.
I see that there is the probability.
What is the probability? I don't see the probability. That's the.
CDF, there is sort of
Yeah.
that x is lower than z, so I think that maybe it's this right side where the z are higher than x.
Where z are higher than x. Z are high. Z is pretty much our choice, because it will be. Let's start by asking the question: what is the probability that the temperature in this room, that will be our unknown variable x, is below, and now we will set this z value, is below 15 degrees. Yeah. So in principle, okay, let's say that the mean value of a temperature in this room is, I don't know, 22 degrees. So 15 would be somewhere here. So we will place our z, let's call it z1. And now we want to know, we have some statistical model of a temperature in this room, and now we want to know what is the probability, given this statistical model, given that we measured and fitted some distribution to the data. We will see that hopefully today how to do that, but it's no big surprises. Just calculate the mean and standard deviation, and we have this curve. So now, what is the probability that the temperature is between negative infinity and 15 degrees, whatever the negative infinity means? Well, the function is telling us the CDF is telling us we should do the integral. So basically, we should calculate and count all the relative probabilities. So the area under this curve will give us some number. Maybe as before. What was the when we were plotting some function that we didn't know how it looks like. What will be the lowest possible value of this function? This is probability, yes. So that's the one which we intuitively know what are the lowest and highest values. So what is the lowest probability? And what is the highest? Good. So let's first just mark it. We will make sure what the about the value of 1. Okay, so if I would now select z to be minus infinity, I probably get the integral from minus infinity to minus infinity. That will be 1. So there is 0 chance that I will have minus infinity as a temperature in this room. How will this function look like? Because of course, if we say CDF is an integral of PDF, what does it mean? How can we reverse this and not have integral but derivative in that sentence? So if CDF is integral of PDF, then exactly. So PDF we already know. What do we know? It's above 0. Yeah, it's definitely non-negative. That means the slope of the function here is definitely non-negative. So the function can either be what? Increasing, decreasing, or constant. Which of these? If something has a positive slope, positive derivative, it's increasing. Or if we are, for example, at the extremes and we have asymptotically 0 probability density function, then it will be constant. Perfect. So it can be only increasing, and that's probably where we can already draw our first point. So Z1. Let's say we continue and we draw and we, let's say our x bar is our second point, Z2. Z2 is here. So we would again do the integral from minus infinity to Z1, and now we will also add the integral from Z1 to Z2. We definitely need to have higher probability at this point. Maybe I will just... Nah, that's not good. Yeah, something like this. And what is so special about this point Z2? We have the maximum value of PDF, so the maximum slope. Yeah, what would the function do? It will even continue increasing after we pass this point, but what? It will increase slower and slower. Yeah, this is the actually the inflection point where we have the highest possible slope. Exactly. So the function should go something like this. Should be more symmetric. Yeah, something like this. Nice. So if we have some other, maybe Z3, that would also mean that we are adding everything from minus infinity until the Z3. So now back to the temperature and this statistical model. what is the probability that there is a temperature lower than 15 degrees in this room? This and that, 20%. What is the probability that the temperature is less than 20 or 22 degrees? Well, around 50%, something like that. What is the probability that is less than 25? Well, the probability is higher because it also includes the 22 and 15, so we are getting closer to 90 or even 100%. Clear? Your faces do not look very friendly to this subject of statistics, but we are nearly done with it. The value of 1, or the 100% probability. Well, what does it mean? It means that if I plug in the value of infinity or whatever very large value, well, that means I'm calculating now the integral from minus infinity to plus infinity. And minus plus infinity, blah blah blah, and it should be equal to 1. And maybe it's really not that obvious that if I will integrate this function or even this function, all the functions will do it from minus infinity to infinity, I will get a value of 1. I will not. And that's why we have this magical constant here, and actually if you calculate this integral, you can maybe try it in MATLAB. So if we have, okay, I should show you, right? Here I practice with some function, but we can make it simpler. So e to the minus x divided by 2, right? That's the one. This works. E to the, I should have another, the bracket is not correct, right? Because I don't want to square the e. This one will be better. Now, just check me, if it's from this distance, everything looks correct. Good. How do we do the integral? Do I have something in memory? Ah, yes. Okay, very handy. So, what is the value here? From minus infinity to infinity, let's just see and calculate. Ah, thank you. That's why I'm saying you should check it. Exactly, yeah. Thanks a lot. Let's see yeah, that's more like it. I saw this number already somewhere. Good, so square root of, what is it, 2 times pi. 2 times pi. Of course, there is some error of integration, but yeah, it is that function. So this magical constant here is here just for having the CDF to be a real probability which goes from 0 to 1. And it would work, now we have done it for mean value of equal to 0 and the standard deviation equal to 1, but it works for any value. Okay. So now we know what to do when we have when we are asking the question, what is the probability that something, that my random variable is less or equal some specific value. And in the more practical applications, we want to maybe look at the questions, what is the probability that the value of my random variable is between this and that. And that will lead us very quickly to something which is called confidence intervals. Does it ring a bell? Confidence interval spolehlivosti. Okay, that does. So let's try it. Let's try it here. What do we want? So either we say, we will say it generally, or we can plug even some values. If I plug 0, it doesn't really matter. It works for all the numbers. If the number is 25, it means the bell curve would be just shifted to the to be centered at 25. Good. So this is our PDF. Yeah, this is our nice bell curve. Yep. Now the thing is, I don't know, have you heard that some years ago, maybe it's already like 10 years, when there was in the CERN in Switzerland, they were doing these experiments, neutrinos, quarks, the Higgs boson. Do you remember? Maybe not, but they were always saying we cannot call it a discovery unless we measure it with the probability of plus minus 6 sigma. Something like that? Nah. Okay, we will try that. In practical applications, we are talking about our random variable lying in some interval plus minus 1 sigma or plus minus 1 standard deviation, plus minus 2 standard deviation, plus minus 3 standard deviation, which really means, of course, if we look at the standard deviation, or so sigma, not sigma square, not the variance. The standard deviation lives somehow in a very similar world than x. Yeah, here we are dividing x square and sigma square, which somehow suggests that x and sigma would even have the same units. And that's what we can now start drawing and asking ourselves, what is the probability that whatever this statistical model represents, that our temperature, our random variable, lies in the interval the mean value minus 1 sigma, mean value plus 1 sigma, yeah? Because, I mean, even somehow graphically, intuitively, if you look at it, this is a relatively high portion of the probability. It's quite likely, it's quite probable that our temperature, pressure, whatever, will lie in this interval. And we can, of course, continue. Minus 2 sigma x bar plus 2 sigma plus 3 sigma minus 3 sigma. So if we would have, let's say, our already standard normal distribution, with mean value equal to 0 and the standard deviation equal to 1, or also also the variance. Yeah, we have the 1, minus 1, 2, 3, minus 2, minus 3. So we can already ask what is the probability that our x lies between x bar minus 1 sigma x bar plus 1 sigma. These 1, 2, 3 are the standard numbers or the standard characteristics, and we will see why, because we will calculate this x bar plus 3 sigma. Okay, what is our probability distribution? Just for repetition, we have 1 divided by sigma is 1, so that's easy. Square root of 2 pi e to the minus x minus x squared divided by 2. Yeah, that would be the standard one. But whatever values of x bar and sigma we have, we just easily plug in. So let's try to calculate this in MATLAB. Where is the MATLAB? Ah, there you go. Okay, so let's say here that our function is what? So our x mean, I will do it generally. Our x mean is 0, our sigma is 1, that's right, and then our function would look like what? I definitely need 1 over sigma, 1 over sigma and over square root of 2 times pi, 1 divided by sigma divided by square root of 2 pi times e to the, now it's time to mess up again, the brackets, xm, this one should be squared, right? X minus the mean value, that is squared, and that must be divided by 2 and divided by sigma square. Sigma square. Come on. Okay, perfect formula. It fits the width of the screen. Yeah, something like this. Watching me? Good. Yep. And now let's do the integral. And now we will integrate from, let's say, minus sigma until sigma 0.6826. That's the probability. So we can mark down our first result between plus and minus 1 standard deviation. We could expect to find 68. What was it? 68.27 realizations, values of our random distribution, of our random variable. Let's say plus minus 2 sigma 95.44. And 3 sigma for completeness. $99.73. So 99.73 is already pretty good number. Yeah, you would probably all agree that it covers most of the values that we can really expect. Whatever is beyond that is something which is not very probable, which is something which we might call outlier. Just maybe for the, so what do the not the physicians, but physicists call a discovery. So if it covers 2, 4, 6, so there is 8 nines in the decimal places. So only the probability of this is considered to be certainty, to be the discovery. Do you still understand what I'm talking about? English and math, both? OK. 95, áno. Ne. 95. Okay, let's maybe have it a bit more colorful. So this will be the so-called 1 sigma interval. Two sigma. And 3 sigma, of course. Where is the 3 here somewhere? Don't know where to draw this. Okay, let's do it here. Well, and basically this is the basics, the fundamentals of the statistics. We will use some of these. We will need one more function that will consider the CDF. Now, of course, the question might be, okay, I just measured, let's say, a flow rate, the height in the tank, the temperature in the room. Well, I have data. Where is the e to the power of minus x squared divided by 2 sigma squared? Well, the nice thing, if we just clear all the maths out of the picture, software can do the math for us, but we need to understand the math before. Then, of course, if we get some data, we got some data. How would our data look, for example? Well, let's say in the simplest example, let's start with the simplest one, that we just measured one stream of data, let's say temperatures. So we have data which is in the form of some data points, x1 to capital N. So our I goes 1, 2, capital N. How do we find x bar? you know this. It's and it doesn't. You do not need to do any integral. Yeah, we do the. Yeah, we do the arithmetic mean. Or we sum it up. We sum the values of x up, and we divide by the number of n. So let's say should I have k or I? This is what I'm always fighting. Let's maybe have k as our index. We would need to do less switching of the notation. So if I take xk, I sum up all the temperatures. Basically, I find the mean, the arithmetic mean, aritmetický priemer of some population of some data. Strictly speaking, what we just got is just an estimate of a mean. Estimate of x bar. So when we are talking about the estimates, maybe you already had it in the theory of automatic control or somewhere else, we would usually put this what is this kind of roof over x. So this is estimate of x bar. That's why it has this hat on top, because of course the real x bar, we actually have a means to calculate it if we know the statistical model. So if we know the probability density function, we would just integrate it, but we will not. This starts to look similar as a cumulative density function, cumulative distribution function. So if we do this, we of course get 1. But if we weigh this integral with a value of x, so we have x here, so we will be counting what if our x is close to the mean, this will have a higher weight. This will be a higher number. Yeah, that's the maximum of the PDF. If our x is close to negative infinity, well, this is close to 0. So this is the actual formula. So this is the formula for getting the mean, and it's also called first moment of a statistical distribution. This thing here is just an estimate, and it's usually called a sample mean, because we only had a couple of samples to get this value. Yeah? Po slovensky sa toto volá stredná hodnota populácie. Tam sa vlastne predpokladá, že máme vlastne populáciu ľudí, lebo človek môže skúmať, že máme koľko ľudí na Slovensku je nižších ako 180 cm, alebo čo je pravdepodobnejšie, čo je najpravdepodobnejšie, že či človek má výšku 160 cm, alebo 180, 190 a podobne. Čiže to sú tie skutočné, a toto sa volá, že výberová stredná hodnota, pretože iba z tej populácie, teraz tuto jak sme, neviem, či by to bol úplne férový výber, by sme vybrali, zmerali výšku nás a na základe toho by sme spočítali, že to je priemer. No asi by sme sa nedostali k najlepšiemu výsledku, lebo neviem, či úplne reprezentujeme celú populáciu napríklad Slovenska alebo Európy. Hej, asi tak. OK. And what about the standard deviation? How do we calculate that? You've done that in your physics labs. Or maybe let's have the variance. Yesterday I had a lecture here for the with the first year bachelor students, and they had this e-learn page where they were inputting some values for the physics lab, and they were counting the relative error and whatever stuff. So you have done it. You know where it is somewhere in your notes. You just cannot recall it now, right? In principle, this is very simple and nice because it starts very similar to the mean, and it actually is a mean. It just doesn't calculate the mean of the temperatures, concentrations of the x. It calculates the mean, the average of this expression. So it calculates, well, if I take my data point and I have the mean, whether it's estimated or whether I know it, I subtract these two and I square them. I basically get the distance. Yeah, how far is this number from the mean? And now I'm calculating just the average number. So how distant are the values of temperature from the mean? And that's basically what we have already seen with this bell curve, because if our variance, right, that was this exercise. If our variance was larger, so this curve was wider, then on average we had higher distance of the values of x from the mean. Okay, and just to, this will of course be called sample, what is it, variance? Maybe some of you recall that during in your physics labs you used to put n-1 here. Does anybody recall that? Okay, there is a reason for that. We will get to that, but for now, let's have this value. So we have hat here, and the variance. Again, it will be calculated very similarly. X minus x bar PDFX. So if I for some reason want to calculate it from the statistical distribution, and basically, well, these are the definitions. Square. I'm missing. I knew I was missing something. And what the English would even have, they would take this. In the beginning, I said that the expected value, the mean value is also called the expected value, and the literature even uses this as an operator. So the x bar will be nothing else than some expected value of x, and here should be capital X. So that's the expected value of x, that's its mean value. This one is the expected value of what? X minus x bar square. And this is then of course called second moment, because there is this square root here. This is like x to the first power, that's why first moment. This is x to the second power. So how much of this was this new how much of this was this trivial. Pretty new or 50-50? Okay, good, good. Good. Thank you very much. Do you have some questions? Question is, where is my lunch? Okay. So, thank you very much. What should I say? I should put this thing on?